The feeling that our technology capabilities are outpacing battery physics is a familiar frustration. We carry devices with massive processing power, yet they die before lunch. The energy wall seems unbreachable until now. A new magnesium-tin alloy has achieved 1,300 hours of operational life, boosting performance by more than 400 times compared to pure magnesium. This is not just another incremental upgrade. It solves a fundamental crystallographic trade-off that has kept advanced portable AI and electric vehicles tethered to the charging port for decades. The breakthrough lies in how researchers at Tohoku University turned a chemical weakness into an engineering strength, creating a stable interface where none existed before. For years, magnesium batteries promised a future of higher energy density than lithium-ion systems without the geopolitical scarcity or safety risks associated with current chemistries. Magnesium offers 170% more theoretical energy storage per unit volume while being far more abundant in the Earth's crust. Yet, for all that promise, the technology remains stuck in laboratories unable to scale beyond proof-of-concept status. The barrier was not a lack of ideas, but a physical reality known as the kinetic energy wall. When pure magnesium is used as an anode, it reacts aggressively with standard electrolytes, forming insulating surface films that block ion flow and cause rapid corrosion. This forces engineers to rely on high-temperature solvents or aggressive chemical environments incompatible with portable devices or consumer vehicles. The result was a battery that either failed instantly or required operating conditions too dangerous for everyday use. The new solution flips the script entirely by embracing rather than suppressing these interfacial reactions. Instead of trying to stop magnesium from reacting, scientists engineered an alloy specifically designed to harness those interactions in a controlled manner. By forming a stable Mg2Sn compound, they created a crystallographic lattice that regulates internal chemistry with unprecedented precision. This design promotes uniform ion deposition during charging and discharging cycles. The outcome is a dramatic suppression of the insulating surface films that previously plagued pure magnesium anodes. In practical terms, this allows the battery to operate at room temperature without degrading into corrosion or short-circuiting due to dendrite formation. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This stability enables a 1,300-hour operational lifespan in controlled testing environments. That figure represents a 400-fold improvement over what was previously possible with pure magnesium anodes under similar conditions. The MgSn intermetallic structure provides the mechanical integrity needed to accommodate volume expansion without pulverization. As ions move in and out of the material during use, the alloy expands and contracts smoothly rather than cracking into useless fragments. This is a critical distinction for electric vehicles which undergo constant thermal cycling and vibration stresses that would destroy standard magnesium components almost immediately. The architecture effectively bypasses the kinetic energy wall by stabilizing the interface against specific crystallographic mismatches that cause failure in liquid electrolyte systems. However, moving from laboratory success to industrial reality introduces significant engineering hurdles that cannot be ignored. While the chemistry is sound and the physics are favorable, scaling this solid-state architecture presents a formidable manufacturing challenge. Creating the precise alloy interface requires tight control over material composition and processing conditions that differ significantly from established lithium-ion supply chains. The production of Mg2Sen anodes involves complex steps to ensure crystallographic uniformity across large batches. Any deviation in the ratio or structure can reintroduce the very degradation mechanisms the design aims to eliminate. This manufacturing complexity remains a bottleneck for rapid adoption, as current facilities are optimized for different chemistries and require substantial retooling investment. Furthermore, the impressive 1,300-hour benchmark comes from highly controlled laboratory testing that does not yet account for real-world operational stresses. We lack comprehensive data on long-term degradation under the extreme thermal cycling and mechanical vibration inherent to electric vehicles or high-load AI edge devices. Portable AI applications demand rapid charge-discharge cycles at varying temperatures, while EVs face years of exposure to road conditions and weather fluctuations. The transition from a stable lab environment to these dynamic real-world scenarios introduces variables that could alter performance characteristics over time. Engineers must now validate whether the crystallographic stability observed in testing holds up when subjected to decades of simulated wear or actual field use. The shift toward solid-state architectures is a critical enabler for this technology's viability, as it relies on the electrolyte's ability to stabilize the interface against specific failures. The magnesium-tin anode works because the solid electrolyte prevents the formation of insulating layers that occur in liquid systems due to crystallographic mismatch. This makes the solution not just a material science fix, but also an electrochemical architecture problem solved through precise material engineering. It represents a fundamental change in how we approach battery design, moving away from trying to contain reactions toward orchestrating them at the atomic level. Yet, this sophistication comes with cost implications that must be weighed against the benefits of higher energy density and improved safety profiles. Ultimately, this breakthrough offers a genuine path forward for overcoming the limitations plaguing current portable power solutions. The ability to operate safely at room temperature while delivering superior energy storage changes the calculus for device designers and vehicle manufacturers alike. It suggests a future where battery size is no longer the primary constraint on AI capabilities or electric range. However, the journey from this promising alloy to widespread adoption depends entirely on solving the manufacturing puzzles that currently stand in its way. The physics are sound, but the engineering of scale remains an unproven variable for now. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.